the outset, we are just going to start off with the definition, okay, the basic definition. So in this particular unit, you are going to come across three terms. One is called the grand canonical ensemble, micro canonical ensemble, and just canonical ensemble. Okay. So before we go to that, we need to understand what is an ensemble. So I'll keep it simple. As I told you that the book that you can usually follow is Patria. Okay. So if you check Patria, you'll basically get all these definitions, and a very good book for statistical mechanics, world renowned. Okay, and then you can definitely go through it, and then you can understand it even better. But I preferably have not taken any kind of long notes here. I'm just trying to make you understand it from a very simple point of view. And also, as far as your exams is concerned, if I ask you what is an ensemble, you should be able to write it from whatever I'm explaining. Okay, should not be very difficult. So these images should be more or less clear to you. So, as we have studied your first unit and second unit, we were more or less dealing with a thermodynamical system. So whenever you got a system, you basically do have some parameters like pressure, volume, temperature, number of particles, okay, and so on. Okay. So we do have that, and I think I should replace it with maybe E. Okay, I think energy is there, volume I've written it twice. Okay, energy is there. And then apart from that, we also have some other parameters. For example, let's say the chemical potential, the Gibbs energy, and so on. Okay, so these terms you might be already known to you, which are important. So these certain parameters that I'm talking about will define a system. So consider a thermodynamic system, or consider a general system. Let's say we have some gas which is enclosed within a box, okay, or within some closed chamber. That will actually have some kind of pressure, some kind of volume, some temperature, energy. The number of particles might be fixed if the system is not allowed to interact with the surrounding. Okay, so that is what we call as a system. But then imagine you have got one system, okay, and you are dividing it into the, let's say you have got this is one system, and you are bringing in all the systems which are similar in nature together. So you are bringing in all the systems here. So how many are there? One, two, three, four, five, six, right? So there are basically five systems here, and all of them might have a similar property. Like all of them will have the same pressure, volume, temperature, energy, number of particles, and so on. This is called an ensemble. Okay, this is called an ensemble. So if you go by a dictionary meaning also, ensemble is nothing but in a way you can say it's a gathering. Okay, so you have these systems, and they are different systems, but then they do have same parameters. Okay, same parameters. So it's not that all the parameters will be same. Depending on which are the parameters which are same in this system, we will have different types of ensemble. Okay, so if I'm considering that we have an ensemble of system where it is A, B, C, D, E, F. Okay, they might be any kind of ensemble. Okay, depending on what are the parameters that are constant there. It's not that every parameter will be constant, so we have to understand that. Okay, but then there is a condition, which is a very important condition to say whether a system is ensemble or not. Okay, the first condition is it should be macroscopically identical system. So if you have pressure, number of particles, energy, volume, temperature, and so on, other parameters, same for all of these. Okay, you basically call it as a macroscopical identical system. So if you remember in our last not last, I think at the beginning of statistical mechanics, we did discuss what is the basic difference between micro and macro. Okay, so if you are basically having a system which whose overall property, let's say the volume, pressure, temperature can be measured, we are basically measuring the macroscopic property. Okay. On the other hand, if you have a system where you have the gas molecules, okay, and you're finding out the velocity of one of the gas molecule, okay, or you're finding out the degree of freedom of one of the gas molecule, you are actually studying the microscopic property. So when we're talking about a macroscopic property, we do say that all of them will have a similar macroscopic parameters. Okay, so pressure, number of particle, energy, volume, temperature, all are more or less nothing but the macroscopic property. Okay, that's important. And the second important condition to understand an ensemble is we call it as it should be an independent system. So you see, what happens is that all of them will have a similar parameter, but they will be independent of each other. Okay, this is not going to affect this. B is not going to affect C. Okay, or C is not going to affect F. There is no effect of one system on another system. So they are more or less independent in nature. Okay, so in general, it will not interact with the surrounding. Okay, and it will also not interact with each other. So it's a very closed system. So if you consider, let's say, a thermos flask, okay, the company like Milton and all, you get it in market. Basically, that can be considered as a system, but that is also not a very perfect system because eventually the water gets cooled down, right? It is meant for keeping the water cool or the warm, right? But then it eventually cools down, so it does have some kind of interaction with the surrounding, and eventually the temperature falls off. So if vacuum is created, there are two probably. One of the better technique is actually make two layers, okay, and in between there will be it will be insulated. Okay, so air is a good insulator. Even if there is an air, basically the flow of heat from this end to this end will be difficult. So that kind of system can be considered to be a closed system. Okay, practically at least that can be a practical example. But then here, whatever we are studying, we are seeing that it is so closed that eventually with time also the property is eventually not going to change. Okay, so that's important. So if you look into the types of ensemble that are possible, there are usually three types of ensemble. One is the microcanonical ensemble. Next is the canonical ensemble, and the third one is the grand canonical ensemble. Okay, and we are going to look into the property of each of these ensemble one by one. Why we call it micro, when we call it canonical, and when we call it as grand canonical ensemble. So what we can do is we can start with micro canonical ensemble, and as I said, micro and macro is important to understand. So you have a system, you measure the pressure, volume, and other quantities. You are basically doing a macroscopic measurement. But when you consider a single molecule here or a single atom here, okay, and you are studying their property like velocity, or you can study degrees of freedom, okay, of one molecule or one of the atom. You're basically studying nothing but the microscopic property. So let's just get back to ensemble now and try to understand what do I mean by microcanonical ensemble. Okay, so look into this. You have this system, okay, and you are dividing it into, let's say you have got a system which has got a energy of E, volume V, and number of particles N. And you are taking all such systems and bringing them together and enclosing them within a rigid enclosure. Okay, so this enclosure is rigid, so it is not movable. Okay, it's very robust, it's rigid, and this enclosure also does not interact with the surrounding. Okay, so each of these systems, so one of them is a system. Okay, this is a system, this is a system, this is a system, and all of them combined together will give you an ensemble. Okay, so you have got this system, and then between these two systems, can they interact? The answer is no. In grand canonical ensemble, it should be impermeable. So what is the importance of impermeability? Okay, if it is permeable, then what happens? The chances are that if the a number of particle n is here in this particular box, okay, and if the wall is not impermeable, and if this is n, again, the chances are that the particle might travel from this end to this end, okay, if it's not impermeable. So impermeable actually relates to a constant value of n. So n does not change because of its impermeability. Okay, and then I think it's quite obvious, you understand why it is insulated. Okay, so if it is insulated, there is no change of temperature. Okay, the temperature does not change. So insulation, so the temperature variation will be nil. So it is rigid, it's impermeable, and it's insulated. That's the first condition for getting a microcanonical ensemble. Okay, so you have to remember this. Okay, and whenever you explain in exam, you can just explain it in your own words. I don't think it's very difficult. But then the point here is that you should remember the keywords here. So rigid is a keyword, impermeable is a keyword, insulated is a keyword. Okay, and that is the first condition which we can use. Okay, and the second condition is, of course, if you want to talk about a microcanonical ensemble, कि the energy, the volume and the number of particles सबको same रहना है, ठीक है? So it's like the all three parameters does not change for any of the system, will remain constant. So as I said at the beginning, that ensemble doesn't mean that each and every thermodynamic parameter will remain the same. No, that's not true. Okay, it might be that these three parameters, just like the energy, volume, and the number of particle, will remain the same. Okay, so if these three parameters remain the same in all these systems, this is a microcanonical ensemble. Okay? In similar lines, we can also talk about canonical ensemble. Okay, we can also talk about canonical ensemble. So let's just have a look into a canonical ensemble now. The logic remains the same, but then some of the properties definitely changes. Okay, so we do have the wall which is more or less rigid. Okay, so this wall is rigid, so rigid will remain here. Okay, probably I can just use the word rigid again. Okay, I've not written it there. So rigid. Okay, so it's rigid. Okay, so the wall will remain as rigid, not going to change anything. It's going to be a conducting wall now. So if you remember in the microcanonical, I said that this was insulated. Now this is going to be conducting wall. What is the reason? Because in canonical ensemble actually is given, the name is given to such system where the temperature, the volume and the number of particles remains the same. So if the particles are not exchanged between the system, it will remain an impermeable wall. So that is fine. Okay. Then volume will remain the same, depends on the number of particles, right? And then we are taking a fixed size, so it's same volume. But what about temperature? So it might happen that all these systems will have a different distribution of temperature. Okay. So if I have a conducting wall, okay, then eventually the temperature of the entire system will more or less be same, right? So if you take a glass of hot water, okay, and keep it in open air, okay, in your room, eventually you will see that the temperature of the water will be equal to the temperature of the room, right? So that means the heat has been distributed. Okay, it's not that you have lost any heat. Okay, the heat has flown into the atmosphere, the heat has been distributed. Okay, and imagine your room is insulated from all sides. Okay, then if you do a very perfect, very precise measurement, you will see that the temperature of the room as well as the temperature of the water, okay, if you compare them, the temperature of the room has slightly gone up. Okay, depending on how much heat has been released from that water, uh, uh, water glass, right? So this is what is the importance of conducting wall is, that there should be conduction, but then that conduction is only valid for exchange of heat or exchange of temperature, but not exchange of particles. So it is impermeable, but then conducting. Okay, so that's important. And then for canonical ensemble, temperature, volume, and number of particles should remain the same, and that is the logic behind this. Okay, next. Finally, we are going to talk about the grand canonical ensemble. Okay, so grand canonical ensemble, if you remember this term mu, this is the chemical potential. Okay, if you remember, this is the chemical potential which you might have come across. And apart from temperature and volume, it should be having a chemical potential which should be same for all these systems. Okay, so if it's temperature, that means the wall should be conducting. Okay, I've just put it in the other way. The wall should be conducting, so it will basically assist in keeping the temperature constant. And the wall should be rigid. Okay, because you know, I don't want any exchange with the surrounding and all. Okay, so this outer wall should be rigid. Okay, that is also very important. Okay, and these walls should also be more or less rigid, so that the volume does not move. Okay, so you know, rigidity also has something to do with the volume. If it is not rigid, then what happens is that the chances of having a greater volume in one of the system might be more. If it is rigid, the volume will remain constant. All the walls are fixed at that particular point. And finally, it should be permeable. Now the question is, it's not impermeable anymore, it is permeable. Okay, this permeable wall results in equalizing the chemical potential. Equalizing the chemical potential. So the chemical potential is same for all the system. It is only possible if it is basically having a permeable wall, not an impermeable wall. So you see, if I ask you a question from here, let's say even a multiple choice question, you might find it a bit confusing, okay? But you have to remember what is the importance. What exactly do you mean by chemical potential? You know, potential is the ability of doing work, right? So whenever we are talking about atoms or molecules, they more or less have a basic chemical behavior, right? So the work that is being done by these atoms or molecule, okay, is referred to as chemical potential. So yes, if you go by definitions of books and all, you will sometimes we do struggle with understanding the physical meaning of chemical potential. But you see, if you understand it in a very simple way, you have atoms and molecules, okay, they will do some work, and by the definition of doing work, we know it's nothing but potential. But then it is happening on the atomic or the molecular range, we're basically calling it as chemical potential. So that's just a name that has been given, okay, for, so it basically remains as potential only. So in all of these cells, the work that is being done by the molecule, okay, transfer of heat, there is some work done. So if it's a, permeable system, the chances are that there will be a transfer of number of particles, okay, and eventually all of them will be in equilibrium state and will ultimately get an chemical potential, okay. So if I just mention you the main points here, if you want to differentiate, what is the differentiate between the microcanonical, canonical, and grand canonical ensemble, you can differentiate it in this way. First, you can write down the name of all these three, okay? So, and then you can talk about which are the parameters that are constant, okay? So that's why I've just not written this. So probably I can just write it down, okay? So what I will do is I will just make a table here so that all of us can easily understand this, okay? So uh, you see, table के लिए जगह ढूंढना पड़ेगा, रुको, कहाँ बना, यहाँ बना थे, okay? So this is okay, right? This is fine. Okay. So what we can do is we can write down the ensemble type. Okay, so this is your ensemble. Okay, so what are the parameters which will remain same? We can write it down here. Okay, so these are two important parts. Okay, okay, and then condition, right? Condition. So when you write down in your exam, and if there is a difference being asked, you can always make it in the form of a table. Okay, so the first one is microcanonical. Okay, the second one is canonical. The third one is grand canonical. Okay, so the first one will have EVN, right? Canonical will have TVN, and the third one will have TV mu. Okay, so if you just look into this difference here, okay, if you just look into this difference here, okay, so see, energy, okay, will remain the same here. Here there is the extra factor which is nothing but the temperature. So as soon as temperature comes in, it will basically be a conducting wall, okay. And when we talk about a grand canonical ensemble, we are talking about the chemical potential. So if the chemical potential needs to be same in all these systems, the number of particles cannot remain the same. So that's why we don't have n here, we have got a mu here, okay. So if you look into the condition here, all of them should be rigid, okay. So I think this is a common property that all of them should have. All of them do have something which we call as rigid. Okay. So this is rigid, this is rigid. Okay, so pen got a bit cold, it seems. Not moving smoothly. Anyway, okay, this is rigid, right? And then, you know, if the number of particle remains same, then you can easily say that it should be impermeable. I'll just write it down, imperm. Okay, so you can make it out. And this is also impermeable. So I would suggest all of you make your own slides, okay? Make your own notes, make your own table. That will be easy. This is permeable because it's chemical potential and it should be there, okay? Okay, then this one, it should be insulated because the energy remains the same. You know, if the heat changes, the energy will change. So this is insulated, right? This is insulated. But here, the temperature should eventually be equal for all the systems. So it should be conducting. Conducting. Okay. So conducting is important here, and this also should be conducting. So I think you can always make a table of your own to understand or remember the difference between these three types of ensemble. What can be the possible question? What are the types of ensemble? What is an ensemble? What are the different types of ensemble? Differentiate between all three of them. So I think this is a very easy approach. If you read Patriya, you will see that the book has given a lot of explanation, a lot of examples has been taken, and then you can read them through. Okay, that has been done from a statistical point of view. Like they have written that, okay, I have a system of n particles, so the total energy will be summation e to the base I, where I goes from 1 to n, those kind of explanations. Okay, so I will also take up that approach, but then I thought that at the first class of this unit we should understand the very basic and the importance and how to remember each of them. Okay, and this is important for even for your entrance exam. Statistical mechanics, although it doesn't get you that many marks, but then these kind of questions are more important and more prominent. Okay.